Today I'm going to talk on this paper about constructive predicativity and sort of predicativity in the way this notion is embodied in Martin-Löf type theory and in constructive mathematics based on this foundation. This is a joint work with Einstein-Klev. So, thanks. So, as you know, the concept of predicativity arose in the context of the debate about paradoxes and foundational mathematics between Poincaré and Russell. And they made observation, the outcome of their analysis of this was that all this paradoxical construction involves circular definitions, in vicious circle in the definition. So this idea led to the formulation of the vicious circle principle in Russell's work as a criterion of predicativity. This is probably the most familiar criterion of predicativity. But in Poincaré writings, there are two other criteria. One is connected to the idea that the mathematical universe for the predicative mathematician should be considered as a potential construction. And so in this sense, there are some collection, and the main example is the collection of real numbers that cannot be considered as completed or actual collection, like in standard set theory. In this sense, they should be regarded as open-ended collections. But there is also another criterion formulated by Poincaré, which is the criterion of invariance, which say that a collection is predicatively acceptable if it is not altered by the introduction of unit. The idea here is that you have a kind of stability with respect to the extension of the mathematical universe, or in a more formal sense with respect to extension, possible extension of the theory. So from the very beginning, there were different criteria of predicativity, and it is not obvious that these criteria converge in some sense, so that they characterize the same portion of mathematics as predicate. Then the study of predicativity developed mainly from the 50s and was related to several important results in mathematical logic, for instance, recursion theory and definability theory, and probably the culmination of this line of research can be found in the proof-theoretic analysis of predicativity given the natural numbers, which was first proposed by Kreisel and then completed by Feferman and Schütte. Now, this conception takes the structure of natural numbers as given together with the full induction principle. So in this sense, we are not analyzing the natural numbers, we are taking them for granted. And then we analyze what we can define in a predicative way over the natural numbers, over the structure of the. So there is an important conceptual point in this analysis, is the fact that the concept of predicativity must be analyzed relatively to a given base. And by this, I mean the principles and the notions assumed as free. And so different choices of the base might yield different conception of predicativity. But this proof-theoretic analysis is probably still today the most robust characterization of predicativity, in the sense that various formal systems which have been introduced with the aim of capturing predicative mathematics can be reducible to this to the ordinal characterized by Feferman and Schütte. And this work was, as I said, initiated by Kreisel in the sense that in this paper, Kreisel proposed a general methodology of autonomous progressions of theories to characterize foundational standpoint. And one of the foundational positions considered by Kreisel was predicatives. The idea is that we start from a base theory T, and then we can ascend to a stronger theory, T of alpha, whenever alpha has been proven to be a well-ordered at some earlier stage. So this is the idea of autonomy. This is a kind of bootstrapping condition. If we prove at the previous stage that a certain alpha is a well-ordered, then we can iterate the construction up to this alpha. And so the problem was, what is the limit of this iteration? And the result by Feferman in another paper by Schütte was that the least upper bound of such progressions is the ordinal gamma naught, and this was considered as the limit of predicativity in this sense. So predicativity is given the natural numbers. But around the same years, there was also a more generous or liberal conception of predicativity, which was proposed by different authors. Probably the main text about this notion of generalized predicativity are in Lang paper from the 50s and 60s, and also in Lorenz and work. And this idea of generalized predicativity can be seen as a rather strong extension of the predicative standpoint. Basically, the idea is that generally inductively defined domains, for instance, constructive ordinals, can be accepted as predicative. And the informal or conceptual motivation is that these generalized inductive definitions introduce new domains of objects by specifying how to construct them from below, and so without resorting to actual infinity. This is the motivation that you can find, for instance, in Lorenz. Now, the theories that and features this kind of inductive definition are usually not predicative according to the Kreisel, Feferman, Schütte analysis. And indeed, in Feferman paper about the proof-theoretic analysis of predicativity, Feferman considers this conception, and he argues that this conception of predicativity is a distortion of the original sense of the concept, in the sense that when you are inductively defining a set, the only way to make sense of this definition, a more formal way, is to represent this set as the smallest set which satisfies a certain closure condition. So in this sense, the definition is obviously circular. And this is essentially the idea of just forming an inductive definition that in an explicit form. So set theoretic analysis.
Sorry, can I ask? May I ask?
Oh, yes. Yeah, sure.
Sorry for going back to slides, but if you go one further back, and sorry, one more.
Okay.
Here. So this paper from 1998, predicativity is what is implicit in accepting the natural numbers together with, and this I read as arithmetical comprehension, right?
Yeah.
So that's just ACA 0, but they go higher, right?
Well, that's the idea of the that you characterize what is implicit in accepting.
And it's the idea that if you unfold ACA, then you go to
exactly.
Okay. So there's a formal result by Feferman about this, right?
Yeah. There's unfolding analysis different from the but it's the same characterization.
But then it depends on how you unfold it, right? So
I think when Feferman, this is not the paper about unfolding. This is the book in the light of logic. And according to Feferman, I think this formulation is best way for introducing the idea of predicativity given the natural numbers.
Right.
Then you can have different formal implementation of this idea. One is the unfolding, but at least I think according to Feferman in this book, in the light of logic, is not collection by Feferman.
Yeah.
It is that essentially the unfolding process should give the same results as the old proof-theoretic analysis.
Thank you.
Okay, so I was speaking about this generalized notion of predicativity. I think another important point is the use of generalized inductive definition in constructive mathematics, especially in this monograph by Martin-Löf, Notes on Constructive Mathematics. And this is very important work because there are a lot of the ideas that were developed later with constructive mathematics, or they already appear in this work. For instance, the point-free approach to topology. You can see that by applying this systematic use of generalized inductive definition, then you can give a constructive analysis of many powerful mathematical constructions. For instance, one of the examples in topology is the for set. And so, but at least in this work, there is no connection with predicativity. This was just an important example of the use of generalized inductive definition in constructive mathematics. Now, the aim of our work is to discuss this notion of generalized predicativity within the context of Martin-Löf type theory. First of all, because Martin-Löf type theory can be considered as a theory, a formal framework for general inductive definitions. And since it allows a huge variety of inductive definition within a dependent type of the structure. And in Martin-Löf type theory, there are several forms of inductively defined notions. You have ordinary definitions by induction, like the type of natural numbers. You have forms of iterated or generalized inductions constructed in ordinals, and you can also generalize this kind of construction. You have inductive families like the identity type, and you have also induction recursion, and the main examples are the universes, the introduction of universes in type theory. And moreover, I think it's also important to stress that you can give a general formulation of inductive definition in the form of schemes. Now, for our analysis based on a particular presentation of type theory, which is called the higher level presentation, I guess that you first introduce a logical framework, which gives this hierarchy of either types. You have a type set, and then higher function type. And you should think of the logical framework as the minimal machinery to introduce the inductively defined types, which are called sets. Now, this type set and the higher function types, they are not inductively defined, but as we will see, they are explained in terms of inductively defined type or sets. And the idea is that, for instance, in the case of the type set, that this is an open concept, because we can always extend our stock of sets or set forming operators by laying down the relevant rules. However, the general constraint is that we preserve the local inductive structure of sets in the sense that every element of sets should be inductively defined in a very general sense of inductive definition. Also, in the case of function types, they are not explained, since they are not inductively generated, we cannot explain them by specifying how they are constructed, but they are explained in terms of their application behavior. So it means that to know that a certain function is an element of the higher function type means that we know how to evaluate the application of that to an argument for these functions. And so you have in this kind of this presentation of type theory, you have two notional functions. One is the higher function type, which is part of the logical framework, and this one. And then we have a derivative notional functions, which is on the level of sets. Here phi AB is a set, since it's an element of the type set, and this can be considered as an inductively defined notion, and the difference essentially is clear when you look at the elimination rule, because you can give the elimination rule as an induction principle. And so it's better to understand this set B A of B as the set of codes for the functions, while the functions are on the level of the logical tree. So they are the hybrid functions. Now there are many examples of sets of inductively defined structure. Natural numbers, of course, is the paradigmatic example of an inductive set. Then you have constructive ordinal, that is third clause, where you have functions. The idea is that the function is encoding sequence, and then the sort of the sequence is a constructive ordinal. So you can give the rules for generalized inductive definition in this form. Then you have also the construction of the universe. The universe should be understood as a set of codes for sets equipped with a decoding function, which takes a code in the universe and gives you the corresponding set. There is the example in the case of the natural numbers. I will introduce n as a set, so I can form the code of n in the universe, and then I can decode it to the original set. Now, the idea is of this analysis of the generalized predicativity is that for every object that we can introduce in constructive type theory, we can generate the corresponding construction tree. And this tree displays how the object A has been built up from the. So this was the informal sense of generalized predicativity. The proposal by Lorenz, for instance, and Alba. But here we can build the tree associated to the object, and this makes excluded all the objects that A presupposes or depends on. And so there is some intuitive level, there is a connection with the notion of predicate. Now, essentially, there are two principles of construction for the tree associated to an object. And the first case is where alpha is a ground type, so something like natural numbers or constructive ordinal. And we first evaluate the object A to a canonical form, so to a value, which is something where that has this form C, where C is a constructor, so essentially the form of C is determined by the introduction rule, and B is the sequence of arguments for C. So the first step is an evaluation to the canonical form. Then the root of the tree is labeled by the constructor. So if, for instance, if we are considering the natural numbers and we get something in the form successor applied to some arguments, then the root will be the successor symbol. And then the tree analysis moves to all the subtrees, which are given by the elements, the arguments for C. So you can apply this analysis for generate the construction tree in the case of the ground. And there is the other important case is when we have a function type. In that case, the root of the tree, we start directly by labeling the root of the tree. And then the immediate subtrees are those arising from the application of the function to the arguments. And of course, all these arguments depend on the range of the on the domain of the function. Now, there is a simple example. If we have closed term of this form, we first evaluate the result of from Q plus Q, so we get something in the form of the successor. And so we can label the root of the tree with S, because S is the relevant constructor, then we move to analyze the immediate subtree, which is 2 plus 1. And so the idea is that we proceed again by evaluating this expression to canonical form. Then we look at the form of the constructor, which will be again the successor, and so on until we reach the 0. So which will stop the evaluation. So in this case, the form of the tree is just this one. And you can see that the important idea is that you first evaluate and then you build the tree with corresponding node. Now there is another example, for instance, with the identity function over natural numbers. And if I start from something of the form lambda, so I apply lambda abstraction on the level of sets, this is already in canonical form. And so the root of the tree is labeled by the constructor lambda, and the immediate subtree is given by the function, the identity function. Now, in this sense, this function is a function in the higher order sense, the identity. And so you have to use the second construction principle here. And the idea is that the subtrees are essentially generated by generating arguments for this function, and so you get an infinitary tree in this case. But it's well founded in the sense that every branch is finite. And every branch can be analyzed by using the first construction principle, at least in this case, because you have natural numbers, a function of natural numbers to natural numbers. So in general, the tree of an object could be an infinitary well-founded tree. In this sense, we have infinitary object, in the sense that the construction tree is infinite, yet it still has a finite syntactical form. This is an important difference with all systems like the system considered, for instance, by Wangel-Lorenzen, where this kind of infinitary objects are included by considering infinitary rules. So you move to semi-formal sense. And in general, the inclusion of infinitary objects is what makes Martin-Löf type theory so powerful from the mathematical point of view, from the point of view of formalization. The idea that the philosophical idea behind this notion of infinity is that this notion of infinity should be understood in a potential way. In the sense that, for instance, child of the node in the previous example is constructed whenever an appropriate argument to the function is given. And so the idea is that the trees are constructed branch by branch and not rank by rank. And the order is determined by the order in which the arguments are provided. I want to say also something about the identity criterion for these trees, because as you can imagine, we call them the same tree structure for different objects. And so, and we want that this construction tree faithfully represent the construction process of the object. So we cannot assume that the identity is simply the fact that two trees have the same structure. And so the correct identity criteria is to say that two labeled trees are equal if and only if they are isomorphic, and their corresponding labels are definitionally equal. So you are asking for a strict notion of equality on the labels, not just consider the abstract form. Now, the construction tree of an object displays all the objects on which A depends, and so all the objects involved in its construction. So in this sense, there is a double kind of dependency. Ontological dependency, because the tree represents how the object is formed. But there is also another kind of dependency, which we may call semantic. said that the object depends on its value. And essentially the construction tree displays all the dependencies of an object only after all semantic dependencies have been described. This is essentially the fact that you have first to evaluate the object in canonical form and then you build the tree. So you have these two notion of dependence. But the analysis of the object in terms of construction tree shows that the object is practically acceptable in the sense that the vicious circle principle is not violated in the construction of the object. Essentially, the fact that these three well-founded structures and the fact that they display all the objects on which A depends, this guarantees that A does not depend on itself, and so in this sense, the vicious circle principle is resolved. And in general, we can use this analysis to indicate the idea that general inductive definition can be understood directly without resorting to the explicit set-theoretic characterization. And essentially, the idea is that now we have an analysis for inductive definition, which works in a sense uniformly. If you are considering something like simple like the natural numbers or more complicated inductive structure, you can explain the fact that this structure respects the vicious circle principle by constructing the associated tree. And so this is a bit can be considered as a reply to Feferman argument, because of course an inductive definition is predicative when analyzed theoretically, but that's true also for the natural numbers. The only reason for which you don't consider natural numbers predicative in the proof-theoretic analysis is just because you take them for granted, so you don't need to analyze them. But in this way, we get a more uniform analysis of inductive construction, and at least we believe that this gives a way to understand this notion in a primitive way, without using the set theory in the background.
But so if I'm Feferman's advocate, wouldn't I just say something like, but you're still implicitly presupposing that you have some kind of closure condition? Or...
Yeah, but you don't explain the closure condition by means of conventional principle.
Yeah, but like in the back of your head, you kind of do, no? I mean, if you really, what is the nature of induction? It means that the domain generated is the smallest domain. Like,
yeah,
it's all there is. If you spell that out, don't you always sort of come back into this? Okay, but what do I mean? Well, I mean the intersection of all of them, or I mean the smallest set generation, something like
no,
that.
because I mean there is. If you consider first the case of elimination, although I didn't give the elimination rule for the constructor, you can see that there is a kind of operational semantics which is given by Martin-Löf meaning explanation, which gives a justification of the elimination. In that case, you can have kind of worry of a circularity, but in a different sense, in the sense that you can use something like induction on the meta level to justify induction, that kind of, but I don't think that you really need to consider the fact that you are constructing something like the intersection or blah blah blah, which respects it. Because that's, at least, my opinion, that is strictly related to the theoretical understanding of that definition. Okay, and yeah, at the same time, I think Feferman objection is, if I accept that, why should I not accept that also for the network?
Yeah, I think that's a good argument. But Feferman would probably say, well, I have concrete intuition for the numbers, but for Plinius or it becomes very, very fuzzy.
If you give the I want to say the idea of the construction trees is essentially that it's not that different from natural numbers to constructive ordinals. Of course, if I define Plinius ordinals in the way with the coding, etc., I can see that that's not obvious like the construction of natural numbers. But this idea of using the trees is essentially the fact that there is more uniformity in this construction, and the fact that the natural number structure, that you assume that you have a clear conception of the natural number structure is essentially because it's an inductive structure. That should be the and so that the idea of inductive generation sometimes is the real point which tied to the word structure. Like in that sense, and you can generalize this to other kinds. So the result of this analysis in terms of construction tree is a criterion of constructive predicativity, where a theory is predicative in this sense, provided that the construction tree of an object A is well defined and well founded whenever the A is an object recognized. And a domain is predicative in this sense, provided that D is recognized by a constructive predicative. Now, according to this criterion, not only the inductively defined types are acceptable from the constructive predicative point of view, but also the type set and larger function types. And this can be essentially understood by looking at the way the construction tree for an element of sets is defined and constructed, and it essentially corresponds to the fact that I mentioned that set as a local inductive structure. But what is more interesting is that by using this criterion, we can also see which constructions are not predicative. And so this may be helpful in identifying the limits of constructive predicativity. Now, essentially, that an object is not constructively predicative means that the attempt to build the corresponding construction tree fail. And there are various ways in which this can happen. We have the case of paradoxical constructions, for instance, where we have certain objects of a ground type, but it doesn't reduce to a value. In this case, it turns out that the object is not well defined, and so the tree is not well defined. There is a more interesting example is when you have construction with axioms which lack a direct computational interpretations. For instance, if you extend type theory with the low x to the middle, in general, we have some objects in the theory, some elements for which we cannot compute the value, and so the corresponding tree is not well defined. And this motivates the fact that we talk of generalized predicativity, we talk about constructive predicativity instead of generalized predicativity, because at least for this characterization in terms of construction tree, this seems to be strictly related to the possibility of to the fact that we adopt a constructive logic. And this is also, if you're familiar with Martin-Löf type theory, there's a result, well-known result that when you extend the theory with the low x to the middle, then the theory becomes automatically impredicative in the sense that you can interpret very strong impredicative theory in it. Then there is a third case in the failure of the construction tree, is when the tree might contain a non-terminating branch. And this is the case of impredicative construction, for instance, of polymorphism in type theory. If we assume that I have a set of different forms, so that this is an element of set, this is already problematic because in some sense I'm destroying the local inductive structure of set because I'm defining a set by quantifying over set. And then I define the identity function. You can see that since the function could take as argument any element of set, you can apply this function to the set itself. So if you unfold this and try to build a construction tree, you can see that this generates a loop in the tree. So that in this sense, the tree is not always found. But this is okay in the sense that this is expected, that you don't want that something like this should count as predicative in any conception of predicativity. But there are more interesting examples. One is the construction of the Malloy universe. this could be understood as the type-theoretic counterpart of the recursively malo ordinal. And the idea is that an ordinal is recursively malo if this ordinal is admissible, and if for every recursive function in alpha there exists an admissible ordinal beta that is closed under. So this is the characterizing property of a malo ordinal. So the problem is to construct a universe in type theory which reflects this malo condition. Now, if we try to write this definition in the type theory, you can see that this is not a positive inductive definition. So in particular, it has a look at from a theoretical point of view, it has a non-monatomic behavior. But there is a line of work which aims to render this construction acceptable in the generalized sense of predicative. The first is a work by Kahle and Setzer in the setting of explicit mathematics. And then this construction of explicit mathematics has inspired other attempts in type theory, in particular attempts which the idea is to, in this two papers by De Beer and Setzer, is to justify this construction in a predicably acceptable way. So this is the main idea behind the construction. And this is just the case. There are two variants of the malo construction. One is the external malo universe, which in the case of type theory means that we are equipping the type set with a malo structure. And the other one is the internal malo universe, where we build this universe as an element of set. So in this sense, and I will discuss mainly the first construction. Now, the idea is that we start from a type of family of sets. So essentially, this is a pair given by an element in set and a family over it. And when we have function from family of sets to family of sets, this can be decomposed in two functions. The first takes a set and the family and gives returns a value in set. Second one as a third argument, which is the value of G applied to the set and the family, and gives again an element in set. Now, the malo condition for a set is the following. Given two function defined as above, so two function, so you can think of the two function like just a single function within the family of sets. There is a sub-universe which is closer than the fixed function, and this is an element of set. So this is the formation rule for these universes. And then the introduction, I didn't include the introduction rule in the slide, but just let me say that the introduction rule reflects the idea that this U is close under G and H. So the image of this image of G and the image of H are again in this universe U. Now, the problem is, can we justify this construction in a practical way? And we can consider the special case where the two functions are the two projections. Because if you go back, this type is a sigma type. So we have pairs as elements of the types, and so it's natural to consider the projections. So it takes the first projections, which takes a pairs, and returns the first component of the pairs, which is a set. And then the second projection, which takes three arguments of this form, returns the family of sets over X, where X is an element of the set. And so, since these two functions are like G and H, just a special case of that, we can form the universe closed under this. Now the idea is, can we build a construction for this object? In particular, if you focus on the first projections, which is a function from family of sets to sets. So this function should be defined on every argument, on every element in the type of the family of sets. And in particular, the first element of the input pair, this pair here, the X, could be every element in the set. But so we have also the case in which X is equal to the universe closed under the projection function. And so this is very similar to the case of polymorphs, that you get a loop and a non-terminating branch, and the tree for this universe is not well found. And so, at least according to the criterion that I gave in the previous slide, Manu universe cannot be regarded as constructively predicative. But in the work by Didier and Setzer, they propose to restrict the possible arguments of pi zero, so of the first projection. Essentially, we should not consider all the families of sets, like in the definition of the that I gave but we should consider only those family of sets that are coded by corresponding elements in the universe that we are considering. So the idea is essentially that we don't have to test the function on every element in the set, but only on the elements that we have already considered. And so, in terms of construction tree, this will amount to a modification of the second principles for construction. Because we are changing the way we evaluate the function. I think I'm not sure because they don't discuss this, at least in the last paper. The idea is to simulate a form of partiality of the function, because this is the way the construction given by Callen sets that in the case of explicit mathematics works, because that is a partial set, but here we are in a total set. And so there are some problem in adapting the construction. But so the case of the Manu universe is important, especially in relation to the limits of constructive predicativity. And there are various modes of object formation or using objects in type theory, and they are justified by this analysis. And so this already suggests that constructive predicatism can have a considerable proof-theoretic strength. For instance, Martin-Löf type theory with well-ordered types, which are a generalization of the constructive ordinal. In a single universe, we already have a proof-theoretic ordinal bigger than gamma naught. So we are already beyond the limits of predicativity in the Kreisel, Feferman, and Schütte sense. And the other important point is that many powerful universe construction, like for instance, the construction of our super universe closed under hyper universe, is justified by this kind of tree analysis. So by implementing this powerful construction, we can get bigger ordinals, so greater proof-theoretic strength. But there seems to be some sense a limit to at least to this kind of universe construction, like for instance the super introduction to super universe is an example. And so, in light of many proof-theoretic results on the strength of various versions of Martin-Löf theory, we believe that is natural to conjecture that the limit of constructive predicativity in the present sense corresponds to the ordinal this theory, critical predicative set theory, with kind of malloc condition on the universal set. This theory was, I think, was the origin of this theory was determined by Rathian, and critical predicative set theory is strictly related to the admissible set, and is a informally we can say that is a predicative restriction of classical set theory, is a modifiable set theory. For instance, you don't have the power set axiom and you restrict separation and collection to get the formulas. But there is also another point is that we could try to develop the Birra sets a proposal to modify that case they speak about the meaning explanation, to modify the meaning explanation, and so also the principles for constructing trees. It remains to be seen whether this proposal can be worked out in a more systematic way. And if this is successful, then this will push the limit of constructive predicativity even beyond this version of critical predicative set theory. Because already with the Malloc universe, you need to go to analyze that construction of the Malloc universe. You need to analyze to go beyond this this version of critical predicative set theory. So if we can make sense of this construction, like Malloc universe, and possibly other constructions which are related, and this is also departure from the traditional way of introducing universes in general sets in Martin-Löf type theory. If we can find a way to systematize and generalize the idea by invariant sensor, then we could have an even stronger notion of constructive predicativity. But anyway, even if we rely just on this this characterization in terms of construction of trees, and even if the limit is this version of predicative set theory with Malloc-like condition, this already shows that this notion of predicativity is much powerful than other traditional notion of predicativity in the theory, and especially of predicativity given the natural numbers. And this is also interesting not only from the point of view of the proof-theoretic strength, but also from the point of view of formalization and development of mathematics in this framework, because this is already above the, for instance, the subsystems of second-order arithmetic studied in reverse mathematics. And since we know from reverse mathematics that many mathematical results can be already obtained in weak subsystems, this means that from the point of view of formalizing mathematical practice, these theories of this kind are very powerful and effective. And so there are, I think, two possible future works. One is to investigate this proposal more in detail, see if we can extend the limit of constructive predicativity. The other that I find interesting is to analyze the way the interaction of this analysis based on construction tree with axioms. When you have axioms not in the form of groups, so Martin-Löf theorems, but particular axiom without computation rules, there is a way to justify some form of that axiom in a way that is compatible with this analysis. That will be another line of research. Okay, so I think I can stop here and thank you for your attention.